Hello, today I'm going over electron configuration lecture. Now, what we're talking about here are the electrons that orbit the nucleus of an atom. Since atoms can have many electrons, we have to understand how the electrons are arranged around the nucleus. Okay. Electron configuration describes how electrons are arranged around the nucleus of an atom. Electrons occupy regions called orbitals, which are grouped into energy levels and sublevels. So these are a couple of different types here I'm going to talk about. This is an S, which is a sphere. This is a P, which looks like two squashed spheres. Sometimes they call it a barbell shape, and it could be on different axes. And there's D sublevels, which have four squashed spheres, oftentimes referred to as a clover arrangement. The main sublevels are S, P, D, and F, and each contains a specific number of orbitals. The arrangement of electrons is important because it helps explain the chemical properties and behaviors of elements. So what we're talking about here is when an atom interacts with another atom, it's going to be through the electrons, which are on the outermost region of that atom. That's why electrons are important in how they're arranged, because they can swap and move between atoms. So we need to talk about three rules that tell us how to put these electrons or represent these electrons in different atoms. First is the Aufbau principle. States that electrons fill the lowest energy orbitals available before moving into higher energy orbitals. That's what we're seeing here. For example, electrons fill the 1s orbital before the 2s orbital, and the 2s orbital before the 2p orbital. And what you'll notice is if energy is going up this way, it's not always the s orbital that gets filled first. We've got 1s, 2s, and then we got 2p, and then 3s, 3p, 4s, 3d. So it goes in increasing energy order. And that's what it's showing here, this kind of ladder formation. This creates a predictable filling order that can be used to write the electron configuration of an atom. Following the Aufbau principle helps ensure that the electron arrangement represents the atom's lowest energy level. So if I'm talking about an atom of oxygen, based on this principle, I know how to fill in the orbitals. I know where those electrons are for that oxygen atom. All right, second rule is the Pauli exclusion principle. It states that no two electrons in the same atom can have exactly the same set of four quantum numbers. All right, that's kind of a lot there. It'll be easier once we go look at the example. Because of this rule, each orbital can hold a maximum of two electrons. So you notice the 1s orbital here is going to have two electrons represented by these arrows. And the 2s orbital has two electrons, each represented by an arrow here. When two electrons occupy the same orbital, they must have opposite spin. So the direction of the arrow is indicating spin. You could say up spin for the up arrow and down spin for the down arrow, but they're spinning, literally spinning on an axis in different directions. The principle explains why electron configurations show paired electrons as two arrows pointing in opposite directions. So let's take a look at this first one. 1s looks fine, up arrow, down arrow, good. But then the 2s has two up arrows. That can't happen. This middle example is good, up arrow, down arrow. up arrow, down arrow. So each arrow again representing one electron and its spin. And then the final one here, the 1s looks pretty good. You got an up arrow and a down arrow, but the 2s can't have that. 2 down arrows, that will not work. It breaks some of the laws of quantum physics. Okay, and then the last one is Hund's rule. Hund's rule describes how electrons are arranged when filling orbitals of equal energy level. So now, when we're talking about equal energy level, we're not talking about 1s, 2s, but we're talking about something like 2p that can allow multiple electrons. So 1s and 2s only have 2 electrons, okay? So you're always gonna go first and second. But 2p can actually hold up to 6. It can hold up to 6 electrons. So the question is, how do we fill in those 6? It states that electrons occupy empty orbitals individually before they begin pairing with other electrons. For example, the 3p orbitals are filled with 1 electron each before any of them receives a second electron. That's this first example here. So when we're adding electrons to this 2p, I put an up arrow, up arrow, up arrow before I do any down arrows, before I pair any of them. This one doesn't work because you've paired here before filling that orbital. The third one doesn't work because you have a down arrow here instead of a single up arrow. So it would go first up arrow, up arrow, up arrow, and then down arrow, down arrow, down arrow if we had more to fill in. Okay, this arrangement reduces the electron-electron repulsion and produces a more stable configuration. All right, we're gonna have some practice with this in future worksheets. So let me know if there's any questions. Thanks.